Welcome back, everybody. Learning as a hobby here, broadcasting to you from this new, hot, muggy day in the city that never sleeps. And we're not going to let that hold us back. We're going to do our math for today. I got Terrence Tao's Analysis 1 book here, and I'm going to go through my summary for section 3.5. So let's jump into it. And if you're watching this also, I am going to try and get finally my vlog for June posted today too. So keep an eye out for that. But let's get to the section summary first. Okay, section 3.5 in Tau is on ordered pairs and Cartesian products, which I mentioned in the last video. So let's go through it. All right, he starts with the definition of what we mean by an ordered pair. Let me just move the screen out of the way here. Okay. So this is definition 3.5.1. Like I said, definition of what we mean by an ordered pair. If X and Y are any objects, they could possibly be equal. We define the ordered pair XY to be the new object consisting of X as its first component and Y as its second component. Two ordered pairs, X, Y, and X prime, Y prime, are considered equal if and only if both of their components match. Or in other words, XY equals X prime, Y prime, if and only if X equals X prime and Y equals Y prime. He labels this as 3.5, which I'm sure he's doing so that he can refer back to it in the exercise set when we get around to it. So there is also I didn't write this in the as a note or anything, but he says we'll show that this notion of equality satisfies the notions of equality from Appendix A7. We'll do that in an exercise. I forget which one it is, but so that there's an exercise set for this. Sorry, an exercise question for it. After this, he has remark 3.5.2. Strictly speaking, the above definition is partly an axiom. However, it is possible to define an ordered pair using the axioms of set theory in a way that we do not need any further postulates. Couple things about that. First, he says see exercise 3.5.1 because we're going to do exactly that. And the definition that we're going to see in exercise 3.5.1, I believe if I remember correctly, we actually already looked at in Spivak a long time ago. So when we get to that exercise set, it'll probably look familiar. Helmholtz's naive set theory talks about this too, if you're familiar with that book. But anyway, we'll get to that in the exercise set. Remark 3.5.3. Although we have just introduced yet another usage of parentheses, the meaning should still be clear from context. It's a problem in mathematics. We have only a finite number of symbols that that we use, so that some of them are overworked, I guess. But from the context of the way that we're using them, there shouldn't be any confusion about what we mean by them. But he does mention that as a note here, just to keep that in mind. Okay, now we have the definition of Cartesian product. So this is definition 3.5.4. If X and Y are sets, then we define the Cartesian product, X times Y, to be the collection of ordered pairs whose first component lies in X and the second component lies in Y. Thus, another way of saying this is X times Y is the set of all X comma Y, such that X is in X or Y is in Y, or equivalently, A is an element of X times Y, if and only if A is X comma Y for some X and X and some Y and Y. Right. He just makes a note after this. One can, in fact, show that the Cartesian product is a set, which we'll do in exercise 3.5.1. The exercise set for this section actually is quite a bit longer than the other one, so it's going to take me a little bit of a while this week to get through those problems, but I will hopefully be able to get them out before the weekend's done. I'll talk more about this, the progress and everything when I get to my June vlog, but here after that note, he has example 3.5.5, just to give an example of Cartesian product. If X equals the set containing 1 and 2, and Y is the set containing 3, 4, 5, then the Cartesian product is the set of all ordered pairs where the first component comes from X, the second component comes from Y. That's the set of ordered pairs 1, 3, 1, 4, 1, 5, 2, 3, 2, 4, and 2, 5. Right? do make a note that there are 6 elements in x times y, and notice that there are 2 elements in x and 3 elements in y. 2 times 3 is 6. That should maybe suggest how to find the. We haven't talked about cardinalities yet, but that should suggest a way of finding the cardinality of at least a finite Cartesian product. We'll talk more about cardinalities in section 3.6. And then also we do y times x here in this example, just so you can see that actually you get technically different, not technically, you get different sets here because the ordered pair 1, 3 is not the same ordered pair as 3, 1. So y times x is actually a different set. So here we still get 6 ordered pairs, but they're different ordered pairs. So we get the ordered pair 3, 1, 3, 2, 4, 1, 4, 2, 5, 1, and 5, 2. All right, so just as a note, referring to what I just said before, in general, x times y is not y times x. So in other words, Cartesian product doesn't commute. However, there are similarities. For example, I just mentioned cardinalities. The cardinality of x times y is equal to the cardinality of y times x for any sets x and y. And he says, see exercise 3.6.5. That's the exercise set for the next section. Like I said, in 3.6, he talks about cardinalities. So we'll get to that hopefully next week. All right, another note. Let f from x times y to the set z be a function, then f can be thought of either as a function of one variable. In other words, you take the element of x times y, x comma y, and that the function takes that to the element in z that we call f of x comma y, or it can be thought of as a function of 2 variables, taking x and y to some z and z. Technically, the domains, if we think about them in those different ways, are different sets. We usually just ignore the difference between them because there's a natural identification between those two sets, which he says here. So while technically different notions, we don't distinguish between the two. And we'll mention this over and over again because it's very common to sort of ignore the fact that if you group the elements of either the ordered pair or ordered triple or whatever in different ways, technically they come from different sets, but we sort of pretend that they're the same thing. I don't know if pretend is the right word. They in some sense they are the same thing, in a very technical way. But we'll get to that. I'm assuming later on in the book. But anyway, so for instance, we can interpret addition of 2 natural numbers as the function from the natural numbers Cartesian product with the natural numbers to natural numbers by the sum of n and m is n plus m. Okay, so that's a function of that type. All right, another note, once we have the notion of an ordered pair, x comma y, we can define an ordered triple by, for example, the ordered triple x comma y comma z, we can define to be the ordered pair where the first component is the ordered pair x comma y and the second component is the element z. And then we could, define ordered 4 tuples in a similar way, et cetera, et cetera. But that's actually not the way that we're going to do the construction of ordered n tuples. Instead, we'll use definition 3.5.6, but he just says you could do it that way. And like I said, for us at least, we're going to sort of ignore the technical differences between the 2 types of things. So this is definition 3.5.6, ordered n tuple and n-fold Cartesian product. So in other words, we can take the Cartesian product of any number of sets, as long as here we have a finite number of them. But let n be a natural number. An ordered n tuple, which he denotes either like this, so x sub I between 1 and n. This sort of like sequence notation, but it's a finite sequence because it doesn't go on forever. You'll also be familiar with seeing it written like this: x1, comma dot 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 to xn, right? So this means the ordered n tuple of elements x1 through xn is a collection of objects xi, one for each number I between 1 and n. We refer to xi as the ith component of the ordered n tuple. 2 ordered n tuples, so here we have the ordered n tuple of xi's and yi's, are said to be equal if and only if they're equal component-wise. So if you have, and then also if you have an ordered n tuple of sets, so here capital X sub I going from 1 to n, is an ordered n tuple of sets. We define the Cartesian product, which is sort of, here we have the product operator, so it's a big pi, that's like the Greek letter P stands for product. I going from 1 to n, x sub I is the n-fold Cartesian product x1 times x2 times x3 times, all the way up to xn. Okay, and the formal definition is here. It's exactly what you think it would be. So another note, this definition postulates that these ordered n-tuples and Cartesian products always exist when needed. However, we can explicitly construct them from the set theory axioms that we've developed already. He says see exercise 3.5.2, so I assume we'll be doing that in that exercise. Remark 3.5.7, one can generalize this construction to infinite Cartesian products, but we have to wait for chapter 8 to do that. So in chapter 8, that whole chapter is on some more advanced set theory concepts. I think he does the axiom of choice in there, and we deal with like infinite sets and things like that. So, I mean, we've seen some examples of infinite sets, but like I said, we'll look at that infinite Cartesian products in chapter 8. Okay, example 3.5.8. So let's say that we have these objects A1, B1, A2, B2, A3, B3, and let X1 be the pair set containing A1, B1, X2 the pair set containing A2, B2, X3 being the pair set containing A3, B3, and then we can take the triple cross product, so x1 times x2 times, sorry, not cross product, Cartesian product, x1 times x2 times x3. That's this set of ordered three tuples. Or we could sort of identify it with this Cartesian product. So we take the Cartesian product of x1 with x2 first, and then we take the Cartesian product of that with x3, and we get these two tuples. But you could also kind of think of them as three tuples, right? Because the first component is itself a two tuple. And then we could also do a similar thing, but if we could take the Cartesian product of x2 and x3 first, and then take the Cartesian product of that with x1, and you get these set of two tuples, which again you could sort of think of as three tuples as well. Which again he says right after the example, he says, strictly speaking, these are three different sets. However, they're clearly very related to each other. For example, there are obvious bijections between them, and this sort of gives a hint as to how we could identify these sets so that there's no ambiguity. It is common in practice to ignore the minor distinctions between these sets and pretend that they're equal. So for example, the function f from x1 times x2 times x3 to y can be thought of as a function of three variables, two variables, or one variable, depending on how we group together the Cartesian products. But again, he says we'll not bother distinguishing them here, right? So remark 3.5.9, an ordered n-tuple, x1 through xn, is also called an ordered sequence of n elements, or in other words, you can think of it as like a finite sequence. So it's a list of elements of sets for which the order makes a difference. Right? In chapter 5, we'll introduce the useful concept of an infinite sequence. Chapter 5, I believe, is when we're going to start constructing the real numbers. And remember, in Tau, he does that using Cauchy sequences. So we're going to need the concept of infinite sequence there. Right, but that's further on down the road. Example 3.5.10, if X is an object, then the one tuple containing X, we call that, in parentheses, X. That's called the one tuple, and we'll identify that with X itself, even though the two are strictly speaking not the same object. Right? One is a one tuple containing X, and one is just the object X itself. Here's a proposition. So just to remind you, when I write something like this without a number after it, what this means is Tau kind of says this in passing and just asks the reader to give the explanation. So he says like why in parentheses with a question mark. So this isn't listed as a proposition in the book. It's just a statement, and then he asks you to supply the proof. So here he asks if x1 is a set, then the Cartesian, or sorry, it's the proposition. If x1 is a set, then that should be a then, not the. Just fix that real quick. Right, then the Cartesian product, pi going from 1 to 1 of xi equals x1, and here's the proof. or my proof, because like I said, he doesn't prove it in the book. He asks you to do it. So let f from that Cartesian product to x1 be the function that identifies the one tuple x with x for each ordered one tuple in the Cartesian product. Then f is a bijection, which can be easily checked. I didn't do it here because it's a very simple, verification you could try. But that shows that there's a bijection between the two sets. So there's really no ambiguity in identifying one thing with the other, if that makes sense. Okay, remark 3.5.10 continued. The empty Cartesian product is defined to be the set containing what's called the empty tuple, rather than the empty set. So the empty Cartesian product is not the empty set. It's the singleton set containing the empty tuple. Right? So that's what we mean by the empty Cartesian product. All right. Some notation here. If n is a natural number, then the shorthand notation for the Cartesian product, where I goes from 1 to n of xi, we write using power notation. So we write this as x to the n. You're familiar with this already. If like R2 is the real numbers Cartesian product with the real numbers and so on. Thus, x1 is just the set x if we ignore the distinction between one tuples and objects x itself. Also, x squared means x Cartesian product with itself. All right. He states another fact and asks you to supply the proof. So here, doing that below. So here's the proposition: let x be a set, then x to the 0 power is the singleton set containing the empty tuple. And the proof is just by the definition. So x to 0, we mean that Cartesian product, and we said that Cartesian product is equal to that set. So it follows just from that. Another note here, we can now generalize the single choice lemma, which is lemma 3.1.5, which we went over in section 3.1, which was a while back now, but you can look back at the video when we talked about that, to allow for multiple but finite number of choices. So we're going to extend now the single choice axiom to multiple choice or finite choice. Note that we're not talking about an infinite choice axiom. We have to wait for that until chapter 8, where we talk about the axiom of choice. But here we at least get finite choice now that we have Cartesian products. So this is lemma 3.5.11. Let n be greater than or equal to 1 be a natural number, and for each natural number, I going from 1 to n, let xi be a non-empty set. Then there exists an n tuple, xi, I going from 1 to n, such that, excuse me, such that xi is in the set xi for all I from 1 to n. In other words, if each xi is non-empty, then the Cartesian product I going from 1 to n of xi is also non-empty. Right, and the proof is by induction, so that's how I did it here, because we have some fact that we're trying to prove for all natural numbers, except for 0. It still holds for n equals 0 in a trivial way, but here he says start at 1, so the base step for us is going to be n equals 1 for this lemma. All right, the base step is very straightforward because we have the single choice lemma. So for n equals 1, x1 is not empty. Therefore, we can choose an x and xi by the single choice lemma. Therefore, pick x equals x. We'll call that x1 in x1. Then we get the one tuple x1, which is an element of x to the first power. Right. So that set is that Cartesian product's not empty. Right. And then we go to the inductive step. Assume choice holds for some natural number n, and let x1 through xn be non-empty sets for each I from 1 to n, and consider the list x1, the list of non-empty sets, right? x1 up to xn plus 1. Then we can choose x1 through xn such that xi is an xi for I1 to n by the inductive hypothesis, and we can choose y and xn by the single choice lemma. Therefore, if we then let y equal xn plus 1, then we get the, here I'm writing it as a 2 tuple, but again, you can identify it with an ordered n plus 1 tuple. So we're not making that distinction, right? We're sort of ignoring that technical detail. Then you get the ordered n tuple here, x1 through xn plus 1, which is an element of the Cartesian product, I going from 1 to n plus 1 of the xi's. So obviously it's not empty. All right, and that proves lemma, what was it? Lemma 3.5.11. Okay, and last remark for this section, and then we have the exercises to get through, which, like I said, I won't probably get around to until the end of the week. But here's the remark. The extension of finite choice to infinite choice cannot be done automatically. It actually requires an additional axiom, which we'll talk about in chapter 8, which is called the axiom of choice. All right, and that's basically the summary for this section. Let me just stop the screen share. Okay, like I said, I am going to work on the exercise set for 3.5 this week, but it's probably going to take me a while to do that because I got tests that I got to grade today and some other stuff for my job that I got to do, so I'm not going to be able to even start on it tonight. But I am going to post my June vlog after I upload this video, and then sometime towards the end of the week, I should be able to post the my solutions for the exercise set for 3.5. So thanks for watching, everybody. Do me a favor and hit the like button and the subscribe button and tell me what you think down below. The interaction with the channel helps YouTube to, share my videos with other people so that, we can grow the group. So uh, keep cool out there, everybody. I know it's we're in the middle of a heat wave, so stay hydrated and everything, and keep doing your math, keep doing your science, and I'll see you guys in the next video.